two works. Have you got it? No. Yes. Acha, okay. And then external force, work done due to, let's say, F. The capital F, we have reserved the symbol for the applied force. And as one can see in this particular example, the work force, if you take F dot S, it will be Fs cos theta. In fact, one can resolve the force F into two components. One will be F cos theta and one will be F sin theta. One can calculate the normal. How do you calculate normal? Normal will be, this is W is equal to mg. So since the resultant is 0, so n plus mg sin theta is equal to, W is equal to mg is equal to n plus mg sin theta, or n is equal to mg minus mg sin theta, right? So this is how one can, oh no, sorry, F sin theta. So this is a normal force. Sometimes a question may arise. See, I've shown this force not applied horizontally on the body. It is obliquely. So somebody even might ask that in case you are pulling the body upwards, then maybe the body has a motion not only horizontally but upwards also. You may be able to lift the body. Like, I mean, if I'm able to. So it all depends on how much force is applied vertically, right? If the vertical force is also there, then the motion could be in that direction also, right? Okay. Today we have arranged for the proper this thing notes one can see. So this was a basic diagram. I told you when you actually get to know or come to know what is work done. Okay. Now can you move it further? And then W dot S, W is equal to F dot S. Now see, basically, whenever you are working with vectors, you know that normally we work with Cartesian coordinate system. That means X, Y, Z system. And a vector quantity always has components along all the directions. So that is what, can you move it further? No, upar. Further, I means ahead. अच्छा नहीं बैकवर्ड ही होगा हाँ जी फर्स्ट बिगिनिंग में ओके सो F is equal to Fxi plus Fij plus Fzk is a force, and S, which is a displacement. See, in fact, what we are going to do is that the different books use different symbols, but what we'll do now, of course, I mean, instead of the board, I'm directly going through the Udaan lectures only. So we will strictly follow the symbols used by them. Although, see, for example, they have written the displacement delta xi plus delta yj plus delta zk. Now, normally, whenever you use the symbol delta, it always means small, but here it is not. Here it is not necessarily small. Actually, you could have taken this as xi plus yj plus zk, because the displacement vector also has components, and the displacement is xi plus yj plus zk. But we will take the symbols delta x, delta y, delta z, and wherever we have to take infinitesimal small element or small distance moved, then in that case we will not use the symbol delta x, delta y, delta z. Of course, you sometimes use these symbols also, delta x, delta y, delta z, but that's essentially the same. Whether you take capital delta or take small letter delta, they are same. But in case we have to take a small quantity moving through a small distance, we are directly going to take it as dx, dy, dz. So ds element could be dxi plus dyj plus dzk. So here delta x, delta y, delta z is Delta x, delta y, delta z is basically, they are representing the components of the displacement only, right? Okay. Now, in the particular case, if you like, we can take some example or we can skip it, because uh, as the force is given by Fs cos theta, if the amount of force, magnitude of the force is given, displacement is given in meters, the force is given in newtons, and of course, angle theta could be given some value 30, 60, 40, whatever. So you can substitute and calculate work. And the work is measured in joules, right? The symbol for the work, unit of the work is joule. Okay, you can go ahead. Just wait here. Okay, now we take another example. See here, you can go through the example or I'll read it for you, that will be better. A load of mass m is equal to 3000 kg. Example 2. A load of mass 3000 kg is lifted by a winch. Winch is an arrangement to lift heavy weights. With an acceleration a is equal to 2 meters per second square, find the work done during the first 1.5 seconds from the beginning of the motion. Now you can go to the next picture. Next page, I mean. See, winch always has a rope to which the mass is attached or the load is attached, and you lift it upward. Now, obviously, whenever you use a rope or string, there will be tension in the string, which is written here as T. Now, few things which are not apparently clear, I'll try to explain, although by now you have so much fundamentals from your previous knowledge that you can directly write. Like they have written a relation, tension is equal to mg plus ma. But how does this relation come? See, actually, suppose the tension in the string is T, this is mass m, and suppose it is moving upwards with an acceleration a, and this is mg. Okay, now for this load, the downward force is mg and the tension is T. So applying Newton's second law, and the load is moving upward with an acceleration a. So T minus mg is equal to ma, or T is equal to mg plus ma. So the tension in the rope will increase. If the system is stationary, the tension will be whatever the load will produce. But if the load is moving upward, there is a sometimes conception that when the load is moving upward, the tension will reduce. Not that. Think of a case when the load is coming down. Then you know that because of the gravity, if the load is falling, right? Suppose you take a string and attach a mass to it and leave it free so that it falls down. Then in that case, string will not have any tension because the mass is falling. So this is clear that when you are lifting it up against the gravity and the force get added. Okay, then further, yeah. Then the total, now this tension only is the force. Because of this tension in the rope, the mass is or the load is moving upward. So the force applied on the body is mg plus ma, and then what is the work done? Work done is always equal to force into the displacement. Now, suppose initially the load was at 0 velocity. Then what happens? You must have come across a formula, relation S is equal to ut plus half at square. So initially if u is 0, then S is half at square. Now in the given question, we are saying that the load is lifted upward with an acceleration of 2 meter per second square. So calculate the work done in 1.5 seconds. So obviously in 1.5 seconds, the mass will get lifted up through a distance. S is equal to half into 2 into 1.5 square. So it's a direct substitution. So here this is, and one can calculate. Okay, let's go further. Now, positive and negative work. See, whenever you talk about work, first of all, let me just mention here that, as one can make oneself also, that work is a scalar quantity, right? Work is a scalar quantity because it is a dot product between the force and the displacement. So it is a scalar quantity. So the work may be positive or negative. Now this fact is also obvious, as one can see that because the work is given by Fs cos theta. So depending upon the argument theta, if theta is, of course, there are three cases. If theta is 0, work is 0. That we have already studied. Of course, it is coming later here. And then if theta is an acute angle, then work done is positive and otherwise negative. Next. You need not make notes directly because all this matter is available. And have you got the notes? No, not the book. Okay, fine. Now these two are the cases when the force and the displacement could be normal to each other and the work done is zero. One case is the work done due to normal force, and the other case is when a body is moving in a circular motion. Now you know that when something is moving in a circular motion, then the displacement at every point is tangential to the circle, whereas the centripetal force is always radial. So both make an angle 90 degree with each other and the work is always zero. Now, next, in fact, we are actually learning concepts that what are the various forces acting on a given body and what are the various kinds of works which could be done. Now, whenever you talk about force, there is a work done. Now, friction is also a force, as we know. Now, frictional forces, where do they act? They always act between two surfaces, right? Now, the work done by friction. Now, normally, see, what is meant by negative and positive work done? Positive work done means you do something. This will become more clear when we go to the concept of energy. Actually, when you do, or since your conversion with few terms, I can just mention that whenever work is done on a given body, it actually leads to increasing the energy of the body. But negative work done will mean you take back the energy. Energy of the body is going to actually decrease. So frictional forces, you know that whenever a body is moving on a rough surface, the body tends to stop. So naturally, if the body had certain energy, it will decrease. So fact always comes in mind that the frictional forces always lead to negative work, but it is not the case. There is an example to prove that. Okay, these two figures are to show that, in fact, the work done due to a friction can be zero, negative as well as positive. When is it zero? When something is lying, uh, a block or a body is lying on a surface, and even if you're pulling it, but the body is not moving. Now, whenever you are applying an external force, there is a frictional force which is trying to oppose a motion. So there is a force acting, but since there is no displacement, so the work done due to friction is zero. Of course, it is zero due to external force also. And then if the body starts moving, then the frictional force was trying to stop it, drag it back. Where is the force applied? The force applied is in the backward direction, and the displacement is in the upper. So the frictional force and the displacement are in opposite directions. So the angle is pi. So the force work done will be negative. But then remember, we had taken a case where you take two blocks. One block is lying on a surface and the other block is lying on the top of the other block. Now in this case, when you apply a force on the upper body, then the frictional force on the block A is backward, right? So in that case, it tries to retard the motion of A. So the work done by the friction, when you calculate the total work done on the body A, will be negative. But the frictional force on B is oppositely directed. Why? Because Newton's third law, right? So frictional force here is in this direction, and on the surface of B, it is in the right direction. And in case frictional force is, as we have we solved one problem in previously, if this frictional force is quite high, then the two blocks will move as a single piece. Then they will not separate out. In case the external force overtakes this frictional force, then A may slip over B, right? So of course, in that case, we assume that B is lying on a frictionless surface, right? So, but the point to note is that the frictional force on the B is in the right direction, and the displacement is also in the right direction. So the work done is positive. So the work done is positive. That's why B also moves rightward. Okay. Now, work done due to gravity. Although I mentioned briefly, but here we'll take up detail. Suppose that there is a block which is moving on an inclined plane, and the block has the initial position at this point and comes to this point, and the displacement S is also shown in the picture in the figure. Now the force due to gravity, because we are calculating work done by the gravity, the force due to gravity is always vertically downwards. So if you choose a XY coordinate system, what will be the force? Minus mg j. J is a, so wherever, if you think some new concept is coming or you are not conversant, you can ask for, but I hope you know. So force due to gravity will be minus mgj, because the force is downward in the minus, and we have taken a XY coordinate where X is rightwards, Y is upwards. Okay, now the block starts from here and reaches at this point. So the displacement, can you take the, No, okay. The displacement is delta xi plus delta yj plus delta zk. Further, next page. Then of course work done will be fg dot s minus mg. Now dot product between j and j is 1, but j and I is 0, and j and k is 0. So on the work done, the work will be done only by giving a displacement to the block in the j direction. Okay, so it will be minus mg delta y. Can we go back? Now what is delta y? Delta y is the change in the position. Yeah, change in the position. Okay, now change in the y coordinate of the block. Now y coordinate at this point is named as yf and is this much, and this is yi, the initial y coordinate, and the displacement is yf minus yi, and how much will be that? Minus h, because the body has moved down, and the lower y coordinate, I mean when it takes the new position, yf is less than yi. Okay, can we go further? So that's why we have taken delta y to be minus h, and the work done will be mgh. So the work done due to gravity only depends upon the distance through which the body falls vertically. The other change in coordinates does not matter. Okay. Now work done by a variable force. Now work done by a variable force. Now see, we have taken the formula to start with, to learn. Basically we said W is equal to F dot S. But sometimes the force may not be a constant force. It might be varying from point to point, and the path along which the work is to be done could be random. So in this case, we have taken up an example where F is variable. Then in that case, you know that it becomes integration. So the when you take a at any given point, so that at this particular point, the distance traveled is ds, and the force at this point is F. Then the work done will be F dot ds. And as you go to the next point, the force might change. Although here also we are making an assumption. We are assuming that when you are taking a small element ds, of course, if the force is varying from point to point, then you might say that over the length of the element also the force is not constant. But we assume that the element is too small, and later on we take the element going to 0. That's why the whole thing becomes integration. I hope you understand that point. So it will become F dot ds, and when you go from A to B, the total work done will be integration of F dot ds from A to B. Is this point clear? Fine. Okay, we can go ahead. Now, work done by a spring. Now see, you know that a spring, when it is placed horizontally so that the gravity doesn't come in picture, then if the spring, there is a rest position of spring, this dashed line shows the rest position, then the spring can either be extended or compressed. Now, whenever you stretch a spring, there is a force called restoring force in the spring. What does it do? It tries to go back to its own position. So it is always opposite to the displacement. You are moving the spring rightwards, but the force is acting in the minus x direction. So that's why we take the force to be always. And in this case, if the spring is compressed, the displacement is in the minus x direction, whereas the force will act in the positive x. So the force is always minus kx. Okay. So the force is minus kx, and then the displacement. How to calculate the, and in this, see, there is an example. There is an example where the force is not constant, because so far I was saying that a force F is applied, and we were normally doing those problems where the amount of the force was given. Here we find that in case of spring, the force is minus kx. So it depends upon how much the spring gets extended. So the force applied will become more and more as there is a more elongation or compression in the spring. So the force is a function of a variable x. Although we are working only in one dimension, but when you're working over 3 dimensions, force could be even a function of x, y, z, all coordinates. Okay. Now this is restoring force. So the work done will be Fx, as it is an example for the integration formula which I gave you. So dx is the small displacement. So the work done will be Fk into dx, and integration from xi is the initial position, xf is the final position, and the formula comes. So the work done by a spring force is always negative, right? So it tries to, okay. Now here one can see that this oblique line basically shows you the variation of force with x coordinate, because F is equal to minus ks, as one can see along the vertical axis we are plotting the force, So as x increases, the force is negative, and on the negative x-axis, force is positive. So as the body moves from xi to xf, the work done is, the magnitude of the work done is half into k into xf square minus xi square. And one can make out from this picture that this is nothing but the area of the shaded portion shown in the graph. How? Uh, there are two right angle triangles. One right angle triangle has a base xf, and which will give you the area, and the height is half kf. So the it will be half into how much? K into xf square, and then unshaded triangle half k xi square. So the shaded portion is half k xf square minus xi square. So the conclusion is basically that when a force variation is given and you wanted to calculate, although it's a case of a spring, but we generalize from here that if the force variation is given, then when you move under the action of that force, when you move a body from one point to another point, then the work done will be given by the area under the curve. Okay, next diagram. A more general case is when the force is randomly or arbitrarily varying. So if you want under the action of the given force, which varies as per this curve, if you move the body from xi to xf, it will be given by the area under the curve. So there is an example. This force variation is given. You are asked to calculate the total work done. So one can see that the force is varying. This is a x coordinate. So from 0 to 2, when the block moves from 0 to 2 meters, during that time, the force was constant as 10 Newton. And then the force started decreasing. And when the block was moving from 2 to 4, the force was varying as shown in the figure. And then at 4, the force becomes 0. And after that, again, it remains constant, right? What is the amount of force? 0. But what will happen? The body could keep on moving, because if the body is already moving, Newton's first law, it will keep on moving even if there is no force. And later on, the force is made negative. It changes direction. So the displacement. So how will you calculate the work done? From 0 to 2, the area under the curve is a rectangle having dimensions 10 and 2, plus this is a triangle, right angle triangle. So half because of the right angle triangle. So height is 10, base is 4 minus 2, plus 0 during 4 to 6, and then minus because the force has now become minus, and then 8 minus 6 is the base of the right angle triangle, and the height is minus 5, right? So the total work done can be calculated. Go ahead. Okay. Now a block starts to slip from the top of his. So there is a sphere, right? And which is lying stable, and on the top portion of the sphere, you put some block or small mass, and then it slides along the, it slips actually along the circular surface. And we have to calculate the work done. So it comes from here, and this small mass reaches here and reaches at that position where the angle, the radius makes a angle theta with the vertical. So we have to see that how much work is done. Okay. Now one can see from the figure that initially the small mass was at the position A, and now it is at the position as shown here P. Okay. So we have to see that how much work is done due to gravity. Only the gravitational force is acting. So the gravitational force will be given. Okay. See, first of all, work done due to normal. Now look at here. The displacement is along the circular path. Now what is normal force? As by name, it is normal. So everywhere it will be normal to surface, whereas the displacement is tangential. So the work done will be 0. Go ahead. Okay, let's go back to the figure. That's no, yeah, here. Now when the point reaches here, then there are two components basically. At this point, there are two components of the displacement. One is this vertical component, one is this horizontal component. Now, if this angle is theta, then what is the line PB? PB will be r sine theta, because in the right angle triangle, the radius of the circle makes hypotenuse, and the line PB is the opposite to the angle. So PB will be, if capital R is taken to be the radius of the circle, it will be R sine theta. And this will be R cos theta, right? This angle is theta, R cos theta. So how much will be this? This distance will be R minus R cos theta, or R into 1 minus cos theta. Is that fine? So this distance is along the x-axis. So this is delta x, this is delta x, and this is delta y. And the displacement is delta xi plus delta yj, whereas the force acting is minus mgj, because the force is due to gravity and it is acting vertically down and with an amount minus with an amount mg, since it is in the minus j direction. So we can go ahead. So work done by mg is mg into minus j, because force is acting vertically down, dot, should have written this, r sine theta I, the x component r sine theta I, plus minus r into 1 minus cos theta j, right? Because the mass, when it slips down from the circle, its y component decreases, although its x component increases. If you take the coordinate, I hope it is clear. If you are taking the coordinate system here, then initially its coordinates are 0. This is x-axis, this is y-axis. So initially at this point, the display, we are starting from the point 0, 0. So as a point reaches here, then the two components are, it moves along x-axis and it falls along y-axis. So the y component, as we have calculated, r into 1 minus cos theta downwards, and x component of the displacement, but x component will not contribute because the force is along j-axis, and the final answer as you have shown. Okay, this we can skip, because see, this is the first lecture of the work and power, and there are 3 lectures which we have to cover today. So few problems I'll skip, but you can try to do yourself because they'll become lengthy to understand. आगे बढ़ा दीजिए. This is similar case हमने पहले किया है, force variation given and you have to calculate work done. Then further, same thing. Even if it is not a it's not a proper inclined plane, but it's a plane, it's a surface which is which has a slope downwards, then the work done due to gravity only depends upon the change in the y component of the fall. It only depends upon through how much distance the body falls. Yeah, next chapter. Next chapter. Next lecture, I mean. Work energy theorem. Okay. Have you heard of work energy theorem? आप लोगों ने कर लिया है, इसलिए थोड़ा सा इजी भी होगा करना, ये भी कह सकते हैं यहाँ. Okay. Now you know that whenever you are doing work on a given, suppose there was a block of mass or there was a body on which some force is applied, and we say work is said to be done, right? Now when work is done, of course, first thing is that if the body was initially either at rest or moving, right? It could be both the cases. So let's take the simpler case when the body was at rest. So as the force was applied, there was a displacement. So the body comes into motion. So we want to see that when the work is done, what actually is the quantity or physical property of the body which actually changes. Now to find out that, of course, I mean, it leads to a very important theorem, work energy theorem. What we find is that, see, the work done, suppose that we are working along the x-axis only to make the thing simple. So suppose a force is also applied on the body along the x-axis. So the force is F, x is displacement. So the work will be simply F into x. Now, since we are taking that case when the body starts moving, and of course, under the action of a force, body always gets accelerated. And according to Newton's second law, F is equal to ma. So the work done will be ma into x. So So this is the amount of work done on the given body when it gets displaced by a distance x. Okay. Now you know from your kinematics knowledge that whenever a body is under motion, then there is a relation between the initial velocity of the body and the final velocity of the body and the distance moved. Of course, there are other relations, but here we are not taking into the time factor. So there are two or three relations, but this relation is for the time being relevant to us. So the final velocity is always given by Vf square is equal to Vi square plus 2ax. Now this a from here can be substituted, and you get a from here can be substituted in this formula, and W is equal to max. Okay, ax. What is ax? Vf square minus Vi square upon 2, because Vf square plus Vi square, sorry, Vf square is should have written, actually better would have been that Vf square minus Vi square is equal to 2ax. So therefore ax is half into Vf square minus Vi square. So if you substitute that in the formula for the work, it becomes work is equal to half m Vf square minus half m Vi square. So from here, actually we say that the quantity half mv square, we name this quantity, which is a scalar quantity only, as a kinetic energy of the body. So the kinetic energy of a given body depends upon two factors, the mass of the body and the velocity of the body. And in the given relation, since we are interested in seeing that where does the work go, the work which we say that we are doing some work on the body, work is said to be done. So what is happening to that work? We are seeing that work becomes mathematically equal to difference of two quantities, two similar quantities. One is named as half mvf square, and other is, and they are meaningful quantities because they depend upon, actually what we are doing is that we are applying the force on a given block or given body of mass m, which actually is set into motion. So the work done is the difference of two quantities, half mvf square, which we have of course named as we give it a symbol k, and we name it as kinetic energy of the body. So since we have introduced the term kinetic energy, so I'll not keep on calling half mvf square. So it becomes, and f is a symbol for the final velocity when it moves through a distance of x, and vi is the initial velocity. We are assuming that initially the body was not at rest. So the work done is nothing but the difference of the final kinetic energy and the initial kinetic energy. So this defines the, so this is actually, this statement is quite, an important in the sense that it not only tells you, it gives you so many things. It not only tells you that where does the work go, it is actually used to build up the kinetic energy of the body. Then this statement, such a simple mathematical relation, also gives you the definition of kinetic energy and also defines work energy theorem. So many things only from a simple statement. And what is work energy theorem? According to work energy theorem, it says that the work done by a force changes the kinetic energy of the particle or of the body. So the work energy theorem, somebody says state work energy theorem. The statement is the work done in a body changes the kinetic energy of the body. Okay, this is a statement of the, and sometimes you write work done is equal to delta k, which is a change in the kinetic energy, and then some properties of the kinetic energy. So we say that suppose there is a body moving. So naturally we know that if a body is moving, somebody must have applied some force. That's why it was set into motion. So some work must have been done on the body. So this concept, when it is with us, then we say that if a body is moving, then it is actually carrying some energy. Of course, kinetic energy is by virtue of the motion of the body, because it is half mv square. A general formula is k is equal to half mv square. So it depends upon the mass of the body and the velocity. So the kinetic energy is by virtue of the motion of the body, and the motion of the body is due to the work done earlier. So we say that a body in motion always carries certain energy. And how much is the energy which it has gained when it was initially at rest? So suppose that the body was initially at rest, then ki is 0. Then the whole work done is half k mvf square. So the whole work was done to bring it to the velocity vf. So the velocity vf which the body has attained is due to the total work which was done on the body. Now the conversely also it is true. It actually says that since I'm assuming some knowledge from you, that's why I'm rushing through, that whenever a body is moving and we know that the work was done, that's why it is carrying certain energy. so that energy can be retrieved back. So if a body is moving with a velocity v having a mass m, then if it is, you try to stop it, then it is going to give you back that energy. See, like a hammer, when you take a hammer and strike something, then the hammer hits a nail and comes to rest. Where is that energy going? Half mv square. Difference of energy is half mv f square. So initially the velocity is there, final velocity is 0, so the energy is lost. Where does it go? It is used to strike the nail which goes into the wood. So the energy can be taken back. Okay. Now we will take some examples to based on work energy theorem. So example 1, suppose there is a block. There is a block of mass 4 kg which is dragged 2 meter along the horizontal surface by a force F is equal to 30 Newton at 53 degrees. Okay, this diagram. Let's suppose theta is 53 degrees. So there is a block whose mass is given. It is always a good idea to take numerical values to solve a problem. It gives you more insight. Otherwise, you can work with symbols also. So this angle is 53. Now you will find that in many books, the angle 53 and 37 being used very frequently. 37 degree. Now you know that whenever you have angles 30, 60, 90, you know their sines and cosines. Sine 30 is half, cos 30 is root 3 by 2, and so on. And what is special about the angle 37 degree and 53 degree? Now see, if you go through the tables, you will find that if you find the value of sine 37 or sine 53 degrees, the values come out to be 3 by 5, roughly 0.6 and 0.8, which could be said to be 4 by 5, which is also equal to cos 53 and cos 37, because you know that cosine and sine are related. Cos theta is sine pi by 2 minus theta and other way around. So sine 53. So whenever in some numerical problem you have the figures are given that an inclined plane at an angle 37 or 53 degrees, you can immediately substitute these values. So sine 0 is 0, sine 37 is lesser, so 3 by 5 to remember. Sine 53 will be higher, so 4 by 5. So it is basically coming from a right angle triangle. If you know that from Pythagoras theorem, if you take a right angle triangle whose sides are 3, 4, then the hypotenuse is 5. Obviously, 3 square plus 4 square under root is 5. Then it is found that in this, if you draw such a triangle and measure the angle, it will always come out to be 53 degree. If you take 3 here, approximately 3 here, 4 here, 5 here, it is going to be 37 degree. So sine 37 is 3 by 5 and sine 53 is 4 by 5. Opposite side divided by hypotenuse. So that's why many numerical problems will have angles 37. Okay. So where were we? We were the previous case. We were calculate. There is a block of mass 4 kg dragged 2 meter along the horizontal surface. So S is along the x-axis and the force 13 Newton acting at 53 degree. And the initial speed is 3 meter per second and the frictional coefficient kinetic, because things are under motion, mu k is equal to 1 by 8. Find the change in the kinetic energy of the block, find its final speed. Now, how many forces are acting on the body? Normal force, weight force, external force, and frictional force. So we will calculate work done due to all. And there was a subtopic in between. We skipped that the total work done on a given body is total work done due to all the forces. So here we find that total work done due to the, can we go back on the, okay, this diagram is here. So since the body is moving along the x-axis, work done due to normal force and the weight force will not be there, will be 0 rather. And there will be only 2 work done, one due to frictional force, which will be negative, and one due to the x component of the force, which will be horizontally rightwards. So that is what we have done here. Can we go back? So Wn is 0, Wg is 0, Wf is Fs cos theta. So N is mg minus f sin theta. This is, yeah, I have written already. F sin, in fact, we calculated also. We calculated somewhere normal was mg minus. So, but anyway, no, when we were calculating Wn, we did not require this, but while calculating Wf, we require the normal. So normal is mg minus f sin theta. So the work done due to frictional force will be small letter lowercase letter f we have reserved for friction, capital F is for external force. So it will be minus f, s is not subscript, minus f into s. So it will be f is minus mu k into n, s is 2 meters, and n is mg minus f sine theta. So one can easily calculate the work done due to frictional force, and work done due to the cos theta component of wf will be fs cos theta. So all the quantities can be calculated, and this total work done when you calculate is actually going to give you the change in the kinetic energy. So one part of the answer is find the change in kinetic energy and find the final velocity. To find the final velocity, we know that initial velocity is given and final velocity can be found. You don't have to use a formula v is equal to u plus at. Actually, when initial velocity is given, so initial kinetic energy can be calculated. Change in kinetic energy we know. So final kinetic energy will be change in kinetic energy plus initial kinetic energy. So Vf can be found. Okay, we have further one more example. It's interesting. A block of mass 2 kg is attached to a spring whose spring constant is 8 Newton per meter. The block slides on a incline for which mu is 1 by 8 and theta is 37 degree, not shown here. If the block starts at rest with the spring unextended, what is its speed when it has moved a distance of 0.5 meter down incline? So as soon as you leave the system free, because of the weight, the block will slide down. And we have to calculate things when the block has already moved through a distance 0.5. Okay, see, I can ask you a question. Initially, the spring is unstretched. You attach a block and keep everything on a incline. So the block, first of all, why should the block stretch the spring? Why the block will stretch the spring? Spring gets extended. Due to what force? Due to what force the spring gets stretched or expanded? Mg sin, right. So one can see that the weight of the body is mg and mg cos theta and mg sin theta. So mg sin theta pulls the, now this thing should keep on happening. So spring should keep on stretching. So where does the process stop actually? Why does the process stop? When the spring is stretched, it will not go beyond a certain limit. So things will come to stable end, right? Finally, spring will get stretched by a certain amount and then things will stop. So this part is not a part of the problem, but I'll ask you to calculate that yourself. But why does the thing stop? Why will it will not happen indefinitely? Why it doesn't keep on, the spring keeps on extending or expanding? Why should the process stop somewhere? One person at a time, yeah. You want to answer? इसमें हम फ्रिक्शनल फोर्स नहीं ले रहे हैं. फ्रिक्शनल फोर्स को ओवरकम करके ही वो आगे जाएगा. अभी देखते हैं इसमें फ्रिक्शनल फोर्स लिया है या नहीं लिया. ओके, दैट्स, हाँ या फ्रिक्शनल फोर्स भी लिया है, वो तो खैर अलग बात है. एनीबॉडी एल्स? व्हाई शुड इट स्टॉप? अगर स्प्रिंग के ऊपर एक बार mg sin थीटा फोर्स लग रहा है और वो लगी रहा है लगातार, तो वो उसको एक्सटेंड क्यों नहीं करता जा रहा? Why it does not keep on stretching it further and further? After a certain limit, it is going to stop. I can give you a hint. See, when the spring is stretched, there is a restoring force in the spring, right? We have learned just now that whenever you compress or stretch a spring, there is a force called, which is developed, which is initially not there. So the spring always has a restoring force. So the restoring force will try to stop the process. But in the beginning, it is unable to stop it. So the restoring force is less. But later on, and because mg sin theta component is high, so it stretches the spring. But why should it stop? Now, see, the mg sin theta component is constant because the incline has a fixed angle and the mass of the block is fixed. So mg sin, but you know that restoring force in a spring is not a constant force. F is equal to minus kx. And what is x? The amount by which spring extends. So as the spring becomes longer and longer, the restoring force becomes more and more. F is equal to minus kx. Initially, x is 0. And as you leave the system free, spring becomes extended. So x starts from, let's say, 0 becomes 1 millimeter, 2 millimeter. So x keep on increasing. So a stage will come when f is equal to kx will counteract f is equal to mg sine theta. So at that moment, the two forces will be equal. The force, the downward force on the block, and the upward force due to the spring, which is not allowing it to stretch further. So at that stage, it will become stable, right? Okay, but anyway, that's a different part of the question. Now to calculate, what we find is that initially, let's suppose initial position, wherever the spring was, the mass was, is taken to be 0, and it extends through a distance d. Then the work done due to gravity is mg sine theta into d. And since the spring extends through, because now we are working in a direction along the incline, so the component of the force, gravity force along the incline was mg sine theta. So the work done, and the displacement is also along the incline. So the work done due to gravity was mg sine theta into d, written as mg d sine theta. And due to the spring, it is due to the, okay, due to the normal force. Now in this case, due to the friction. Now this component was mg sine theta, so the perpendicular component was mg cos theta. So the normal force is mg cos theta. So the friction is mu into n, so becomes mu k mg cos theta. And since the block moves through a distance d, the negative force, the negative work done due to friction is minus mu k mg cos theta into d. And due to spring, we have already calculated. We found that the work done due to spring is always negative, minus kx square, right? We calculated initially. So in this case, k, suppose k is the spring constant and the d is the distance through which is the block is moving. So the work done due to spring is minus kd square. Add all the works and then you will find, okay, can we go to the next? And that will give you the total change in the kinetic energy. So total work done is work energy theorem. We are doing problems on work energy based on work energy theorem. So initially the block was at rest. So the change in kinetic energy is half mv square, where v is the velocity. After it travels a distance, d is equal to 0.5 as asked in the problem. And all this, so frictional work, spring work, and the gravity work. So one can calculate and find v comes out to be 2 meter per second, right? And this is another interesting problem. Suppose there is a moving belt. It is there in many factories and companies. When you want to move things out, the finished product, there is a running belt, right? Or even escalator, you know that there is a running belt and we sometimes step on that. We are always try to push ahead and we want to, okay. So there is a running belt which is moving with a velocity v, and you very gently place a block on the belt, right? Now what will happen? Initially the block will not like to move, right? Due to friction also, it will not like to move, but eventually it moves with the belt, right? And there is a, first it will try to slip. Slip means slip back. See, actually, if you look at the, you have to perceive the, there is only one diagram drawn here. The belt is moving rightwards. So with respect to the belt, the block will move backward. Basically, the block doesn't like to move initially, inertia. But, so there is a slipping. So the block slips backward, but eventually the block moves, right? We'll try to understand also that why it moves. And then finally, it moves with the belt and attains a velocity v. So we have to calculate what is the work done by friction. How far does the box, this is a box actually, instead of block, they are saying there is a running belt on which a box is placed. So how far does the box move before reaching its final speed, which is the speed of the belt only. Usse zyada nahi ho sakta. It cannot be more than that. And when the box reaches its final speed, how far has the belt moved? So three things we have to calculate. Now, most important thing to note is that in this case, the frictional force is rightwards because the block is moving due to friction only. Remember the case when we had two blocks A and B kept one above the other. Then the frictional force on the A block was backward, whereas the frictional force on the block B was rightwards. That's why and the in that case, the work done due to the frictional force on the block B is positive, and the block B also moves along with the block A. So the same thing is here. The frictional, because the block doesn't like to move, so with respect to belt, it is moving leftwards. If you are standing at, if you are standing on the belt and somebody keeps a block or box, let me use either of the term. So suppose I am on the belt and somebody keeps a box, I'll find the box moving away from me in the other direction. So the frictional force will be rightwards. And because of the frictional force only, the box is finally going to move. There is a friction. Okay, if there is no friction, what is going to, suppose the friction between the box and the belt is zero. In that case, what do you expect? In that case, what do you expect? Suppose that the friction between the belt and the box which you are keeping gently on the belt had been zero, theoretically. Then what do you expect? It will keep on lying there. The belt will keep on moving below it. Sometimes you do it, you keep a paper and keep a pen and then pull the paper, the pen remains there, right? If you are, the force applied is much more than the frictional, so it will not move. It keeps there and you are able to pull out. You might have done this as a game in your childhood. Of course, you people are still small in age. So the, in that case, block will not move. But in this case, the block will eventually move and finally attain the velocity v. So we have to calculate so many things that after, within the time the block moves, attains the velocity v, how much distance it travels. Okay. Now the problem is comparatively simple as it looks to be. Now see, the work energy theorem says that the work done is equal to change in kinetic energy. Now initially the box was at rest when you were keeping it on the belt, and let's say its final velocity is going to be the velocity of the belt only. So the change in kinetic energy is half mv square, and the work done is half mv square. And how much is the work done? Work done is due to the friction. Now friction will come from normal. Now box weight is mg, so the friction force is mu k mg. And the, after moving through a distance d, the block attains a velocity v. So the change in kinetic energy half mv square is when the block has moved through, where d is unknown to us, we are actually interested in finding d. So we assume that after moving a distance d, the block attains a velocity v. So the change in kinetic energy is half mv square, and up to that time, the work done on the block will be mu mg into d. So equate the two and you are able to get d. So this is the expression for the distance traveled by the block before it attains a velocity v. So look at work energy theorem, helps you in finding a unknown quantity so easily. And then we have to see how much does the belt move. The box is moving through a distance d, but the box was initially at rest and it took time to attain the velocity d, but the belt is always moving. So logically also it looks like the belt would have moved more distance. Now to find the distance moved by the belt, we find that if the box takes time t to reach the speed v, initially the block was at rest, so its final velocity is u plus at. So u is 0, its final velocity is v is equal to at. So this formula actually tells you that to find the acceleration of the box. So acceleration of the box will be given by v is equal to at, or a is equal to v by t. Now in this time, the box moves a distance d. Now s is equal to ut plus half at square. So u was 0, so it moves a distance half at square with the acceleration a, which is v by t. So we don't know a, we don't know t, but that is not our purpose to finally. So the distance moved is d is equal to half at square. Now from here substitute for a, or v is equal to at, तो at की जगह हो जाएगा v, so d is half vt, right? Half vt. So the distance traveled by the box is going to be d is half vt. You can actually calculate the time from this expression. That is not our aim. You can actually calculate the time by which it moves through a distance d, right? It will be given by t is equal to 2d. Okay, now the belt is, by the time the block attains a velocity v, during that time the belt is moving with a velocity v. So how much is the distance traveled by the belt? V into t. The belt moves with a time with a velocity v, and the whole process takes a time t. So the belt will move through a distance v into t. And we have found an expression d is equal to half Vt. So Vt is 2d. So the belt moves through a distance 2d. By the time box starting from rest attains a velocity v, the belt has moved on through a distance 2d. Okay, next. हाँ next कर लीजिए. Next. Yeah, this is ये हमने किया. हाँ ये तो कर लिया. इसके नेक्स्ट, उसके भी नेक्स्ट नेक्स्ट. इससे पहले देखें अगर इसका इसके नीचे क्या है. We can do a particle of mass m moves on a straight line with a velocity varying with distance traveling according to the equation v is equal to a into root x. So it's a case where a body is moving with a variable velocity, where a is a constant, a is not acceleration, is a constant. So v is proportional to root x. Find the total work done by all the forces during a displacement from x is equal to 0 to x is equal to d. Next sheet we can see if we can rush through fast. So work energy theorem, K2 minus K1 is half m v2 square minus half v1 square, and velocity is a root x. Initially at x is equal to 0, the velocity is 0 because velocity is given by a into root x. And after the problem says after the block goes through a distance d. So when the block goes through a distance d, the velocity will be, because the velocity changes with the position. So at the point x is equal to 0, the velocity of the block was 0, and at x is equal to d, the velocity is going to be a into root d. So the final kinetic energy is half m vd, half m d, a square, because the constant was also there, and then that gives you the change in kinetic energy. Okay, हाँ आगे करिए. ये भी कर सकते हैं, वैसे सिंपल है, कोई नहीं. फर्दर yeah, example 4. This is an interesting. Let's take all types of examples. Horizontal surface, and then inclined plane, and then pulleys. So look at the diagram. There are two pulleys over which a rope goes, and there are two masses. To the first pulley, a mass m1 is hanging down, and to the second pulley, a mass m2 is attached. And we are given a condition. Given, okay, let's read the problem. Given m1 is greater than 2m2, so the mass of the block m1 is greater than twice the, so if one is 2 kg, other could be 5 kg, even greater than twice the smaller block. System starts from rest, m1 block comes down by a distance h. Find the speeds of the bodies. Obviously, if m1 is heavier, so m1 will go down because of the gravity only. So m1 goes down. So as m1 goes down, then m2 goes up. That is first to understand. And you know that in such problems, we have done one similar problem earlier, when the mass m1 moves through a distance d, the other mass moves through double the distance. One can simply draw the diagram and calculate. So the distance traveled by the two masses is not same, because the mass m1 is attached to two ropes. So when it goes down, the most left hand side rope becomes longer, and the middle rope also changes by a both change by a length ll. Then the third, the most outside portion of the rope will change by a distance 2l. And because of this, one point which we will consider later, let me just tell you. So if the block m1 is moving down through a distance l, the block m2 will move up with a distance 2l. So the velocities of two will differ. So if the velocity of m1 is v, the velocity of m2 will be 2v. It will be double. Okay. So keeping these facts in mind, problem is so simple to handle. Can you show the solution? Just applying work energy theorem. So m1 is going down. Okay. And the tension, can we go back to the picture? So when we draw the free body diagram of M1 and M2, M1, the weight is downwards and the tension in the string. Now there are two strings T, because two strings are picking up M1. So the tension in the lower string will be 2T. If you draw the, how do you get this answer 2T? This we get if we draw the free body diagram of this pulley. If you draw the free body diagram of this pulley, two upward tensions T are applied and one downward tension, let's say T dash is applied. So T dash is going to be 2T. So 2T is a tension. So on the mass M1, an upward force, because tension is force, an upward force 2T is applied and a downward force M1G is applied. And M1 being heavier is going down. So M1G minus 2T, right? And since it is moving downward with an acceleration, okay, we are not taking acceleration. We are applying work energy theorem. So suppose that it moves through some distance, then, and since the system is starting from rest, so initial velocity is 0, so change in velocity will be half mv square. So suppose that when the system travels through a distance d, the velocity of m1 becomes d, then change in kinetic energy is half md square. And what is the work done? It is coming from work energy theorem, and work done is force into the distance traveled. So 2t into d, rather 2 m1 g into d minus 2t into d. Now let's go back, go through the next page. It is here. Downward, it is moving through a distance h, right? We are taking h. So the mass m1 goes down through a distance h. So the work done due to gravity will be m1 g into h, and work done due to the tension in the rope will be minus 2th, because the tension in the rope is 2t and the rope changes through a dimension h, right? So m1gh, is this point clear? m1gh is the work done on the body due to gravity, and 2th is the work done in opposite direction due to the tension in the string. So the difference of two works is kinetic energy, gain in the kinetic energy. So m1gh minus 2th is half mv square. Why m1g is positive? Because the work done due to the gravity is positive, and in the same direction the body is moving. The case is opposite in the second case. If you want, we can go back to the diagram. The second mass m2 is going up. The second, because when m1 goes down, m2 goes up, right? So as m2 goes up, so in that case, the motion is along the tension of the string and not due to the weight of the, why there is more tension? Because m1 is pulling down that rope. So there is more tension in the part of the string attached to m2. So m2 moves up. So its weight is not letting, of course, its weight is trying to pull it down. So that work will be subtracted. Weight is trying to pull it down, but the tension in the string is so high, it takes it up. So now the next page. So it is T into 2, and that, as I explained earlier, T into 2h, because the mass m2 moves through 2h if the mass m1 moves through h. So T into 2h minus m2g into 2h. This is the work done on the mass m2, and that is equal to the gain in kinetic energy, which is a scalar quantity. So half m2 into, and the velocity will be double as I explained, so 2v square. Now when you eliminate t from the two relations, you get the final velocity of the system. So in fact, not the system, we will actually give you the velocity of m1, and 2v will be the velocity of m2. Okay, next chapter. Next lecture. Potential energy. So we are now on the third lecture. Actually, we cannot spend more time on earlier lectures. So concept of potential energy. Now, of course, few things are known to you, but still to get the concept, see, basically, suppose that we take a ball and throw it upward, right? We imparted some initial velocity so that it moves with velocity and throw it upwards. You know that from your experience or from other physics problems, that it goes up, but meanwhile it is slowing down, and it finally reaches a point where its velocity becomes zero, right? And then from that point it starts falling back, and when it reaches your hands, it's almost having the same velocity with which it started with, right? Almost same, because it's not, it will be slightly less. So we say that initially the body had a kinetic energy, because half mv square is a kinetic energy. We have learned the concept. And then when it is moving up, then what happens to that? Where does that kinetic energy go? Right? Only thing which has changed is the position of the body. So the ball, suppose it was a ball. So ball initially had a kinetic energy, but when it reaches a upper point, its kinetic energy becomes zero. So we say that at that point, the ball has a certain potential to do something, because it starts coming down. So it had a potential to do work, right? Because I've explained to you that work and energy are related. We say that when work is done, the body attains or gains energy, but that energy can be used to get back work. When suppose you have a spring to which a mass is attached, we do some work, and compress the spring. Then to the compressed spring, if you attach some other body and leave it free, it will be thrown away. जैसे गुलेल से खेलते हैं, you know that, or bow and arrow, right? So you know that energy can be used to get back work, right? So both are interchangeable. So here, so when we say that a given body has a energy and it can give you back work, we say that it has a potential to do work, and correspondingly define a quantity called potential energy. And potential energy, as in the case of the ball going vertically upward, is by virtue of the position of the body, right? So when the ball was initially at the ground level and was given some kinetic energy, or take an example, a ball lying at rest on the ground, then it has neither kinetic energy, and we say that with respect to the Earth's surface, of course, that we have to learn, with respect to Earth's surface, its potential energy is also zero. In fact, potential energy, as you will learn eventually, is cannot is a quantity which we don't define absolutely, but always define as difference in the potential energy. So at one, because it is by virtue of the position. So any given body, like when you talk about kinetic energy, you say that it is by virtue of the motion. So a body may be absolutely at rest with respect, then kinetic energy is zero, and when it is moving, it has kinetic energy. But when you say it is by virtue of position, then by virtue of position with respect to, like when you talk about gravitational potential energy, it is because of the gravity. So it will depend, it will matter that with respect to gravity is due to Earth. So with respect to Earth, what is the position of the body? So the potential energy is always a difference in the potential energy between two positions, right? So potential energy is the energy associated with the relative position of two or more interacting particles or two or more interacting bodies. In most of the cases, it is ground and another body of lesser weight. And then you also talk about potential energy due to a spring. So suppose that a spring is at rest and you stretch it, and when you stretch it and leave it free, it goes back. So it has, and you stretch it and it is not moving, right? You stretch it, slowly stretch it. Of course, this concept is a very, I mean, basically, see, whenever sometimes to talk about potential energy, because when we talk about potential energy, then sometimes we don't want to bring in kinetic energy. We want to suppose independent of kinetic energy, we want to learn about potential energy, and we are saying that potential energy is due to the position of the body. Then sometimes actually to learn it, we talk about a hypothetical experiment or hypothetical way by which we generate potential energy. Like kinetic energy is you pull something with a force, it will be set into motion, and kinetic energy, it gets kinetic energy. It's so easy to. But when we say that potential energy is by virtue of position, now although when I'm throwing something upwards, the kinetic energy I'm giving it, which is converting to potential energy, it's a different case where kinetic energy, in fact, when you talk about conservation of energy, as you will learn maybe by the end of today's lecture, that when you talk about energy of a given body, it is not purely its kinetic energy, it's sum of the kinetic energy and potential energy. So when you say energy is conserved, then for a given body, at any given point, you have to take the sum of kinetic and potential energy both. And when it changes position, then you will find that its velocity also correspondingly change and the sum remains same. But in fact, when last time I talked about conservation of momentum, and I told you that collision of particle problems you can always solve through conservation of momentum and conservation of kinetic energy. At that time, I said conservation of kinetic energy. I didn't say conservation of energy. Actually, sometimes what we say is that suppose that you are working on a horizontal surface, then the potential energy will be same. It will not change. So in that case, the energy will be kinetic energy only, because potential energy will change only if it moves up or down. So if you are working on the Earth's surface, two particles are colliding, like you hit a carom coin with a striker, then that is a very good example for this thing where collision of particles, right? So potential energy we don't have to talk about at that time, right? So like a spring, we always take the spring motion. Of course, we had taken an example where the spring was lying on an inclined plane, or you can take a vertical spring also. Then you have to talk about gravity also. But here, when you take a spring on a horizontal surface, then independent, you can purely talk about spring force. Then need not bring in gravity. So suppose that the spring is at rest. This is the rest position, and you pull it, right? Then it changes position, and we say that as you leave it free, it goes back. So it had some energy. That means, so that energy, and since the position of the spring means the mass attached to the spring. So since the position of the mass attached to the spring changed, so it had potential energy, and it had potential to do work. You can get it back. If you were sitting on the spring, you are going to, like, I mean, you can have a swing, you can have a, there are swings which have springs system, springs are stretched and compressed, and you get motion. So it is by virtue of position. Can we go ahead? Something I was telling you in between, I'll slightly later tell you. See, basically, uh, uh, there is one more concept we have to learn actually while learning about potential energy. It is about conservative forces, right? I hope you have heard about conservative forces, right? Conservative forces, by their name, are those forces under which when you do some work, right, the energy is conserved. The energy is conserved. Energy is conserved in the sense, in fact, the two examples of conservative forces are force due to gravity and spring force. Okay, let's do something before actually we talk about conservative forces. See, we give a symbol U for the potential energy. So UB and UA actually tell you about the potential energy of a body at the position B, like we had kinetic energy KB and Ka, potential energy at the position A and B. And as in case of work energy theorem, we talked about change in kinetic energy. Here we talk about change in potential energy. And the change in potential energy as a particle moves from point A to B equals the negative of the work done by the associated conservative force. So this is the definition of change in potential energy. The change in the potential energy as you go from one position to another position, of course, that you will always do under the action of a force, and it is given by minus WC. Can we go ahead to this equation? So it is UB minus UA. The conservative force is given a symbol F subscript C. So, and most of the forces we work with are conservative only. So as we have been using symbol F for force, right? So here conservative force could be spring force or gravitational force. And for example, frictional force is not conservative. I'll explain slightly later. So the difference in the potential energy is given by UB minus UA is equal to minus FC dot ds. And why it is so? See, basically we say that suppose that there is a particle here, or there is a body or block here, and I want to give it potential energy. Now see, there is a block uh, lying on a horizontal surface. Now what is the force already acting on the block? The gravitational force mg. So if I have to lift it up, I have to overcome that force. Now if I give it a force much larger than the gravitational force, it will get accelerated, Newton's second law. If the net force on any given body is non-zero, imparts it a acceleration. So what we say is that in the hypothetical experiment, that suppose we apply a force initially, we start applying some force on it. It will not move because the gravitational force mg, let's say 100 Newton or whatever. If you're applying a force lesser than that, it will not, you will not be able to lift it because the net force is going to be downward. So it is, you can't move it up. So slowly and slowly you increase the force. A stage will come when the force will be equal to the gravitational force. Now at that time the two forces are equal. So the net force on the body is still zero, but it will not move. According to Newton's second law, unless there is a net force, it will not give it motion, right? Now suppose that you increase the force by infinitesimal amount, very small, very small. Now the net force on the system or the on the block will become greater than zero because you are overcoming the weight force and applying a force slightly greater than that. So as you apply a force which is slightly greater than that, the body will be set into motion, right? It will move up, right? But you, and we sometimes say that we apply the force in such a way or by such an amount that we don't want to accelerate the body. We don't want to. So you will say that it will move very slowly, let it move very slowly. Only thing is that we have to take it from one position to another position which is higher, vertically up. So, and we apply the force. So in fact, we always assume that the applied force is equal to mg. This here conservative force which you are applying against that's why the negative sign is there. The gravitational force is downwards, but you are applying a force upward, opposite. That's why I mean, somebody might ask why in the definition you are saying that the change in potential energy of a particle as it moves from point A to B is equal to negative of the work done, whereas in work energy theorem it was equal to the work done. Here it is, why it is negative. So the work done is opposite to the force acting on the body, but you are applying a force in opposite direction equal to that, but slightly delta more than that. So you will say that it is going to take very long time to reach the final position where you want to take it. So the answer is let it take. Our aim is to take it from one position to another position without generating any kinetic energy. That is our aim. So that we only purely talk about potential energy. So we are not generating, although you can take a mixed case when you lift it, both kinetic energy is also given to the body as well as potential energy as you lift it up. But since we want to learn only about potential energy, we do this process. Of course, we are not doing it. We are only learning it. So we will say that we do it so slowly that kinetic energy is not generated and only its position changes. And at the final position, we say that where is the work done? Where is the work gone? That is given to the stored as potential energy, right? So as it goes to, okay, we can further. So gravitational potential energy. So that we can go to the next page. So the work done by gravity on particle of mass m whose vertical coordinates changes from ya to yb will be, so ya to yb, right? So the change in the position is yb minus ya. So the work done is mg into yb minus ya. But as by the definition, we have to take a minus sign. So minus, and since we are lifting up, okay, see there are two minus signs you have to take care. One minus sign is there in the definition. UV minus UA is minus integration FC dot ds. And since gravity is downwards and you are moving the body upwards, so the work, when you calculate the work done, it comes to be negative. So both the negative signs cancel out and finally you get, that's why in the gravitational minus sign, and UV minus UA will be mgh and UV will be UA plus mgh. So you say that if under the action of gravity, if a body is taken from a point A to another point B and UA is the potential energy of the body at the point A, then the potential energy of the body at the point B will be UB is equal to, it is always relative to some other position. So we know that UB minus UA is mgh, but from this relation we don't know what is UB and what is UA. So it is always in relation to some position. Although in case of spring, you can actually calculate the potential energy, because in that case, the example, yeah, it is there further. Spring potential energy, the work done by the spring force is minus, we have already learned, minus K into xf square minus xi square. So in that case, it is final energy is initial energy. Now, when the spring is at rest, it is in the relaxed position. So at that point, let's take xi or x1 to be 0. So the corresponding potential energy is 0. It doesn't have any potential to do work. So in that case, the as it is stretched or compressed, it doesn't matter because the potential energy, or even in that case kinetic energy, which is a even function, because x squared term comes. So in both cases, it has the same potential energy. As soon as the spring gets extended or compressed by an amount x, the potential energy in that position is half k x squared. So k negative or positive will give you the same potential energy. So the potential energy for a spring is half k x squared. We can go ahead. ये उसका प्लॉट ही है, पैराबोलिक फंक्शन हो गया ना, हाफ के एक्स स्क्वायर. Yeah, this is an interesting example. A uniform rod of mass m. We have to read the problem. A uniform rod of mass m and length l is held vertically upright. And then on a horizontal surface, as shown in the figure, find the potential energy of the rod if the zero potential energy level is assumed at. Sometimes we make an assumption. We say that let's assume that on the horizontal ground on which we always work, the earth's surface, the potential energy of every body is taken to be 0. Then, as I was telling you, uv minus ua is mgh. Then we sometimes make the formula u with a subscript h is mgh. So as h is 0, h means height from the surface of the earth. So if u 0 is taken 0, then uv is mgh. So here also in this particular problem, we assume that at the surface the potential energy is 0, since the parts of the rod. Now one can see why this rod should have a energy, potential energy, because the rod is vertically, although the rod is, one end of the rod is on the ground, but the other end is at a height. But the whole rod is not at the same height. Different points are at different positions. So could like a set of small bodies at different heights. So naturally the potential energy at every height will be different. So to calculate the total potential energy, we resort to integration method. We assume that, let's suppose we take a small element of the rod at a height y having a small dimension dy, right? So the small element of the rod which is at a height y will have a energy, potential energy mgy, where m is the mass of that small element. That element has to be taken smaller. Why? Why small element? Because if the element dimensions are large, then even the lower end and the upper end of the element will be at different heights. So we have to take it as small as possible. That's why we take the symbol dy, which means dy goes to 0, which we don't write always. We assume that dy is 0, right? So the potential energy of this element will be, and what is the mass of this element? If the length of the rod is capital L, total mass is m, then as I told you much before in another problem, that we can always talk about linear density, m, capital M upon capital L. So mass of the element having dimensions dy will be m upon L into dy. M upon L into dy is the mass of the element, and the potential energy is mass into gy. So this is the potential energy of the small element, and as you sum up, starting from the small element at the bottom up to the small element at the top. So that means you are taking y from the coordinate y from 0 to L. So integration, and you get the answer u is equal to half mgl. This is how. Okay, I think we can stop here, and then time is already. हाँ 4:47 हो गया, 2 मिनट का ही फर्क है. So we can ask, take questions from outside. No online questions. In fact, I should have said that in between. That is the loss of going through a. This is kind of PPT presentation, because in that case, the matter keeps on running, but if you do on the board, it is slower. See, basically, conservative forces have a property that if you, under the action of a conservative force, if you move a body from one point to another point, then there is a change in the potential energy or change in kinetic energy, depending upon the case. Then, in both the cases, the change only depends upon the end positions. Like you can see from the formula for the spring, minus half k into xf square minus xi square. So what is the value of the initial position and what is the value of the final position? The value of that coordinate only will determine the change in energy. And how you take the body to that point doesn't matter. So it is independent of the path. First conclusion. And second is that if you bring back the body from the final position to initial position, that means you make xf now xi and xi as xf, then the answer will be just minus of the previous case. So that actually means that if you take the body along a closed loop, then the total net work done is zero. So under the action of conservative forces, if a body is moved along a closed path of any random shape, you need not bring back the body along the same path. Only thing is that you take it from xi to xf and bring it back from xf to xi. The work done is given back to you. So the net work done is zero. But same is not true about non-conservative forces. And an example of non-conservative force is a frictional force, right? Now the question sometimes asked is why that is a non-conservative force and gravitation and spring are examples of conservative forces. And they are path dependent because under the friction, if you move something along one line, along other line, the work done will be different. And as I told you that in the case of spring, if I stretch a spring and leave it free, it comes back. So it had a potential, which means potential energy. But suppose I strike something here, it moves along the table. Now, when it goes to the new position, it doesn't come back. So the work, where does the work go? Where does the energy go? Because whenever force is applied, work is said to be done. And whenever work is done, energy is obtained or created, which is with the body, right? Where does that energy go? So the answer is that basically, yeah, you want to answer? हाँ नहीं वो तो ठीक है लेकिन एनर्जी लॉस कहाँ हुआ? See, basically the difference is that in case of friction, it is a contact force. Remember, in the beginning when we learned about forces, there is a force action at distance force. Gravity is action at a distance force. In case of spring also, we are assuming that when the spring is lying on a horizontal surface and when you are moving the block to stretch or compress the spring, then there is no friction with the surface. That is absent. In case there also you take friction, things will change. So in case of spring, and in case better is gravity. In case of gravity, the force is action at a distance force. There is no, but friction is a contact force. And whenever there is a contact force, and when you drag one body over the other, then due to friction, they don't like to move each other. So they try to stop the motion or oppose the motion. So the basically energy is gone into heat energy. It is lost as heat energy. Friction to overcome frictional force. So the energy, it's not a conservative force. So there is no conservation of energy in a way, mechanical energy. Yeah. No questions. Okay, fine then. Okay, thank you so much. Tomorrow, Dr. Ashish will take up the further part. Power part will be introduced later, right?